All right, last time we talked about algebraic data types. About the algebra, the multiplication, which is product types, addition, which is sum types, and we even had 0 and 1 as void and unit, right? But what about minus and division? Do we have negative types? No, we don't have negative types. No, we don't have fractional types either. Okay, so if we don't have subtraction and we don't have division, can we solve equations then? Doesn't seem like we could. But let's try. Let's try to solve an equation. So let me write an equation. Okay, let me say L of A. Okay, does it show on the screen here? Yeah. L of A equals, let's say, 1 plus A times L of A. Okay, this will not compile, no. Right? How would one solve an equation like this for L? Find what L is. Okay, that's a simple algebra, right? So what would we do? Well, we want these two terms to be on the left-hand side, right? So unfortunately, we have to do a division. Right? L of A minus A times L of A equals 1, right? I just moved it to the left-hand side by subtracting from both sides, right? You know, I'm just having fun with this. Oh. So we have 1 minus A times L of A equals 1. And now we can divide by this, right? None of this we could do on types, huh? 1 divided by 1 minus A. Okay. So even though we have addition and multiplication on types, we couldn't really do these operations on types, right? No, we couldn't. But does anybody recognize this expression here?
Power series?
Power series, yeah. Okay, so this is the sum of an infinite series from n equals 0 to infinity of a to the power of n, right? Geometric series. Right? Algebra. Now this thing is only sums and products, right? A to the power of n is A times A times A and times, and they are summed. So this could actually be translated into our type language, right? So even though we did some stuff in the middle that's not available for types, we could still do this and just get the final thing as our, that we can write it in terms of types, right? So what is this thing in terms of types? Well, it's like for the power of power 0, right? That's just unit. Okay, I'm gonna just write it in terms of unit. Then plus is this vertical bar, right, for some type. Then we have A to the power of 1, which is just A. Then we would have A square, so it's A, well, sort of like a pair of A's, right? A product, a pair. Okay, and then we would have a triple of A's. And so on to infinity, right? Something like this. This translates into this funny thing. Okay, now if you look at it, you know, well, this is like a nullary tuple, right? This is a singleton. And this is I mean a single element list. This is a 2-element list. This is a 3-element list, and so on. 4-element list, 5-element list, and so on. So this sum actually encompasses all lists. So this type is actually a list of A type. Because a list of A is a sum of empty list, 1-element list, 2-element list, and so on, right? So that's funny. This equation actually gives us a list. And if you don't believe me that this is really a list, okay, let me solve this equation in a slightly different way, where I'm not using subtraction or division. Okay, I'm using something called a fixed point. Okay, so I'm just looking at this thing here, L of A, right? I can substitute this whole expression for this L of A, right? So this is multiplication here, right? So I will put 1 plus A times, and here I'm going to put this whole equation instead of L of A. So 1 plus A times L of A. Okay? Now let's continue doing the same thing, right? Replace this LA with the whole formula. So this will be 1 plus A. Well, we can actually do the multiplication. So this is A plus A times 1 is A, right? Plus A squared times L. So it's A squared times 1 plus A times list of A. I'm already calling list, okay? So again, so we do the multiplication and we get A squared times 1 is A squared, right? Plus, and here when we substitute this, we'll get A cubed, right? And you know the story. I mean, if you keep doing this infinitely many times, you will get this whole series, right? So that's more of the, you know, within type theory, we could do something like this if we know what a fixed point is. Because this is like, you know, like doing Newton's method to calculate the square root. You just apply the same thing over and over and over until it converges. So here we don't know what convergence is really, but this is an okay thing. So this equation really generates a list, right? So let me rewrite this starting from our list language, okay? And I'll be more careful with naming things. So I will say data, okay, because I'm defining a new data type using this equation, and I will call it list. So that's my type constructor that takes one argument, A. List of A. A is a type variable, right? Now, what is 1? That's a singleton. That's the unit type, right? So a unit type we can construct from nothing. We just have to give some name to the constructor that takes no argument. So let's give it a name. What do we normally call it? Nil? Let's say nil. Okay. So that's this constructor. This constructor creates a unit type. Takes no arguments and just creates a single type. Now plus, of course, becomes the some type or, right? Call it or. And here we have, now this will correspond to a second constructor. So let's call the second constructor cons. Okay, that's traditionally called cons because there was like a assembly instruction in some Lisp machine that was called cons. It sounded crazy like
it was a CDC
yeah?
something or other. Yeah.
Okay.
Car encoder.
car and coulter and cons. No, cons mean. What was the meaning of cons? Construct. Simply construct, right? Cons is an abbreviation.
Yeah, car and coulter were control decrement register and control something register. Accumulation register.
Okay, so the history of the stuff goes long ago. And Lisp was the first language that really worked very well with lists. So cons, we'll call this constructor cons, and it takes two things, right? It's a product, so it's a constructor that takes two arguments. One argument is of type A, and the other argument is of type list of A, right? This LA, that's a list of A. Okay, so this defines a type, right? It defines a type, but in a funny way, because it uses the type it's defining inside the definition, right? So we call this a recursive definition, because it uses itself. It's chasing its tail. Okay?
Would you categorize that as the top is an algebra in function space, and the bottom is an algebra in type space?
Yes. Yeah, it's algebra in type space. It's the typo. What do we call this? The algebra of types. Right? But it's cool that we can do this kind of operations in type space. Even though we don't have subtraction and division. Like if we had subtraction, then we could call it a ring, right? But we don't. So we just call it algebra. So you can actually. Did you write it down?
I did. It compiles.
It compiles. You see? It compiles. So you actually can define your own list in Haskell. Of course, nobody does this, because a list is a built-in type with special syntactic sugar that makes it much easier to use. So the sugar here is, well, it's sort of, this would not compile, okay? But the built-in syntax sort of is like, this type constructor becomes the outfix brackets of A, right? So bracket A bracket, that's the list of A.
It's built-in constructor syntax. I don't think you can override it, right?
No, I said this will not compile, right? So this will not compile, but this is conceptually, this is like, yeah.
The outfix operator.
The outfix operator doesn't compile. The nil constructor is actually called bracket bracket. Okay? This is an empty list. This is a notation for a constructor for an empty list, or just an empty list. Right? And another constructor is actually sort of like a value. And cons becomes an infix operator. So this part sort of would compile, because you can have infix operators. So we put this infix in between these two guys, and it's a colon. Colon is this infix operator that concatenate, the cons is a list. So you can create a list by providing an element and another list, and this other list is called the tail, right? But list was replaced with brackets of A. Okay. So this is an element. This is a tail, head and tail of the list. So you can construct either an empty list, or you can construct a list by providing a tail, which is already a list previously constructed somewhere, and another element for its head, right? And the built-in syntax goes even further, because you can also define literals for these. So, for instance, obviously you can create an empty list by just using this constructor. So that's an empty list. Now, if you want to construct a list with one element, let's say we are using integers, a list of integers. So let's say a list that contains a 1 would be 1 const with an empty list. So empty tail here, right? Instead of this one, I put an empty tail and I const it with 1. So it's a 1 element list, right? And I can continue doing this and say, I want to create a list that is 2, and here's the tail, and my tail is this guy, 1 colon empty list, right? And the thing is that these parentheses are not necessary because colon binds to the right. Okay, so I can remove that. So I have a list that has 2, 1, and this is like a terminator for a list. This terminator. And this notation, sugar for this, is just 1. Okay, string literals are written this way instead of this way. I mean, this is also valid syntax, but this shortcut is this, and this would be 2, 1, right? And then there's even more, because you can create ranges. Like you can say, I have a range from 0 to 5. Okay, what's the thing here? 2 dots. Okay, 2 dots. If you put 2 dots between these things, then you have the whole range from 0 to 5, right? And that works for enumeration types. Okay, so not for every type you can do this, because not all types are ordered like this, but there are types that can be enumerated, and integers happen to be like this. And why not extend this notation and say, I wanted to have a list that starts with 0, but I don't provide the end of the list. What does that mean? It's an infinite list. It's a list of 0, 1, 2, 3, 4, 5, blah, 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 infinity. Okay? Why can I do this in Haskell? Why? Lazy. Haskell is lazy. So if I write something like this, it does not mean that the runtime will start busily, eagerly calculating this stuff, and will just go into an infinite loop forever. Yeah. But if you want to access elements of this list, then you will have to do it one by one anyway. So like if you say, I want 5 first elements from this list, it will give you the 5 elements. And then if you want to like print 5 elements, it will. If you say print the whole list, then it will go into an infinite. Or actually it will abort at some point. Right? So that's the built-in syntax for lists. Now, what should I erase? Okay, let me keep this definition, pseudo definition of list, right? So that we remember, okay, this is one constructor for an empty list. This is another constructor that does const, and this is the data type, right? So now, if we would like to write a function that takes a list, okay? Well, then look at this. It's a sum type, right? On the outside, it's just a sum type of 2 types, right? So the only way to write a function on list is to pattern match on these 2 constructors, right? So this is how all functions on lists eventually can be simplified too, okay? But you have some functions, higher order functions on lists, that internally are implemented. You can use functions that use other functions and other functions of lists and so on. But at the bottom, you always have something that will pattern match on the list. Okay, so let's do an exercise and define a function called empty. And And this is a function whose type is list of A's, and it returns, let's say, an int. Okay, it returns the bool, right? It returns the bool. It says it returns true if the list is empty, and false if it's non-empty. Okay, so how do we implement something like this? Well, so first of all, empty definition. We have to pattern match, right? It's a sum type, so we have to pattern match on the first constructor and pattern match on the second constructor. So pattern matching on the first constructor is easy. Right? Pattern matching on the second constructor. So we have to use the pattern, and I'm going to use the same notation for values as I use for types. And that's a common thing, so I want you to get used to this. That, you know, you say A. In this case, it doesn't mean type A, it means a value of type A. Right? So the second pattern is a cons, it's an infix, right, of A, and actually, you know what? I'll call this X, and this I will call X's. Okay, that's also a very popular notation in Haskell, that if you write an element as X, then a list of X's, a value of that's a list of X's, it's called plural of X, right, with an S. Okay.
Although semantically X colon AS would be better, wouldn't it? Because it's a list of A's, not a list of X's.
Yeah, right.
But nobody does that.
No. I mean, I could put A here and A's here. That's also a possibility. Okay, so now what should empty of an empty list return? Is an empty list empty? Yeah? People are nodding, okay? Let the record show that people are nodding that it should be true. Okay? And in this case, what should we return? False, right? It's non-empty, right? A list that matches this pattern can never be empty because it has at least one element, the head. The tail could be empty, doesn't matter, but at least one element is there. But okay, but notice something. We are not using X or XS on this side at all, right? Hey, so let's put wildcards here. Okay. But in fact, we are not using even this fact that it's a non-empty list. We could just say underscore right here, and it will still work for a different reason, right? It will work because these patterns are tried in order, right? As I explained last time, they are tried in. So if a list is empty, it will hit this pattern. But if the list is non-empty, it will try this pattern, which always succeeds. It would succeed for an empty list, but nobody asks it to match an empty list because an empty list goes first through this hole and comes out on the other side as true. So this is really a very simple thing, right? So underscore equals false. Okay? Alright, but this is like the simplest possible thing, right? Now let's do something more complicated, something that actually does something with the contents of the list. Okay? So let's define a function that we call map. By the way, empty and map are built into Prelude, into the standard library. So you don't have to define them. So map is something that applies a function to every element of a list. Okay, it's like in C++, it's called transform. Okay, and here, so we want to apply a function. So a function has a type from A to B, A arrow B. That's a function that we are applying. And B can be different from A. So, you know, we are taking apples and turning them into oranges. That's okay. Now, the second argument is a list of apples, right? And what will be produced is by applying this function that turns apples into oranges, right? We'll get a list of oranges, which is a list of B in this case. Okay? So we apply this function to every element of the list. Right? That's a nice description, right? So again, well, we have to do the same thing, pattern match. We have to define what map of an empty list is, and we have to define what a map of x colon x is.
Function argument in there as well.
Oh, of course, thank you. Yeah, because we need this argument too. F, right? Okay, I'm squeezing this stuff too much. Okay. It's a function of two arguments, map F, and we are matching on the second argument of this function. So think of map F as carried or already pre-applied thing, right? That's a function of a list. For a given F, it's a function of a list. Right? So, if the list is empty and we apply F to every element of this list, what do we get?
An empty list.
An empty list. And in fact, we are not using this F at all. So in this case, we can just replace it with a wildcard. Who cares, right? We're not using it. This is a more interesting case. We want to return a list whose elements are F acting on X's, right? So first of all, we have to construct a list whose first element, the head of the list, is Fx, right? F acting on X. But now we have to apply F to the tail. How do we apply F to the tail? Okay, and we want to construct a list of this stuff and F applied to the tail. Well, F applied to the tail is map F X's, right? That's F applied to the tail, by definition, right? This is what we are doing. Okay, and now notice, right, we are on the right-hand side of the definition of map, we are using map. So, this is called recursion, right? Do I need parents here?
I think you need them around the map, the second. Yeah.
Okay, the precedence always fools me.
The space is high precedence, so
this binds very, very strongly, right?
yeah.
So this will bind the stuff into one like solid object, right? And this is an operator. Operators have lower precedence, so I don't need parentheses, right? Because this stuff binds like super glue.
I see.
Okay? Yeah, it works? Excellent. Now, of course, think about how would an imperative programmer solve this problem. He would say immediately, okay, if you want, okay, well, let me give you yet another example that's much easier to ask an imperative programmer, right? An imperative programmer. let's say we want to calculate the length of a list, right? Length of a list. So length is something that takes a list of A's and produces an int, right? So an imperative program would say, okay, so you have to have a loop, right? You have to loop through this list. So in order to loop, you need some kind of counter that you would initialize it to 0 and then would add 1 every time in the loop, and you would like follow the pointer to the next element of the list, right? So in some pointer that starts at the head of the list, and then you would use pointer equals next, you know, and so on, and you would have to check whether the next pointer is null, right? Yeah.
So, first of all, an imperative programmer could use recursion. It probably wouldn't do it because it involves.
They would never use recursion for one main reason.
Because it involves sticking stuff on the stack.
Right, it would blow up the stack,
and now
right?
I have my next question,
Uh-huh.
which is, how do we know
that this wouldn't blow the stack?
Correct. How do we know
the implementation that we haven't written yet, right? Okay.
Right. How do we know that the implementation?
No, that's a very good question.
Going to be efficient.
But just wait, okay? Because we haven't implemented it yet, right? Yeah. Okay, so as you can see, the imperative implementation is very detailed. It tells the computer exactly what to do in which order. It introduces these additional variables, initializes them, keeps track of where we are, and so on, right? So this is now let's do it recursively, the Haskell implementation, right? And we'll just say, okay, so we have two patterns to match. Empty list. Length of an empty list is what? 0, right? What's the length of a list that has some x and x's? Oh, it's a single column. Okay, it will be 1 plus the length of x's, right? So, like, people will complain that this is really hard to understand recursion. It's like, this is much easier to understand. It's 1 plus the length of x's. Now I don't know. Okay, this has the highest precedence, so I don't need parentheses, right? This is super glue. Okay. Then that's it. Okay? There is no loop. And this corresponds to our thinking about it, you know? This is very easy to understand. There are no spurious variables. In fact, I can put an underscore here because I'm not using elements of this list. I just want to know that there is a head, and I put 1 for the head, right? So there is nothing spurious here. There is nothing to initialize, nothing to follow pointers. But the funny thing is that this code is converted by the compiler into a loop. Okay? So I have written a loop because a loop is efficient, right? But I didn't have to write the details of this loop. I just say, this is the definition of length. Figure out how to calculate it. Okay? I'm just telling you, this is the definition. So it's like a mathematical definition of length. And go figure. I don't want to play with the details. I don't want to follow pointers and make mistakes, you know, forget to initialize a variable. I don't want mutation at all. There's nothing mutating here, right? It's all constant things, immutable things, right? So there are these two descriptions. One corresponds to what it really is, what we are really doing, describes the idea, and the other describes these little steps that, you know, like the compiler should know what steps to do. We need a higher level language to do this. Now, how it is converted to a loop? Well, it's very simple. It's called tail recursion. Tail recursion means that if you are using the function at the tail of your calculation, then, you know, why not jump to replace it with a go-to? I mean, right? So it will go to the beginning of this calculation with some new variable, and so on. It is not going to use this stack. It's not going to call this function. It will just go to the beginning. Okay? Yes?
This is not strictly the canonical tail recursion because we are doing calculation after compute the length of the tail and then the plus one. You have to call, get the value back, and then you do plus one.
Okay, you caught me there. Yes. Cannot cheat, right? Yeah, you're right. This is really, you first have to descend into this.
So what was the question?
Well, he said that this is not really tail recursion, right? Because you first have to call len and then add one.
The first one is more efficient. That's the one with the tail recursion in it. Tail recursion is when the last function.
Right, but the last one that's done is the addition.
Length and axis.
You still have some complication after you return.
And then you can apply one. It doesn't matter the left or the right.
Yeah,
I think
yeah.
that-
No, it doesn't matter, but in this form you see more clearly that actually you have to have the result of length for the first
I think the
before you add one, right?
version would have an extra parameter in it that is like the current count.
Yes, right, right. So this can be converted into tail recursion, and I bet the compiler does it, right? Somebody tell me that the compiler is smart enough to turn it into tail recursion.
Try calculate the length of billion elements in the distance.
But it's lazy anyway.
Well, that's a good challenge for you.
Oh, you are saying does it take an hour or does it take
No, does
a
it block the
second?
stack or not?
Oh,
What's the question? You want me to try something else?
so try to calculate.
million.
So this is the build. Well, okay, I don't know how the built-in length is implemented, right?
Find out.
So 1 to a million.
Yeah. Okay. So
That was pretty quick.
that was very quick.
And then the
To a
built-in-
million, right?
Yeah.
Okay.
Obviously difficult to.
So
set-
calculating the len of a million element list was very quick.
I don't know if there's an easy way.
Well,
to
I
time
don't know.
functions.
But it's not time that we're concerned about, it's blowing the stack up.
Can you add a few more zeros?
Sure.
No, but this will overflow the integer.
Well, actually, this is specialized
To
to
a billion.
This is specialized to integer instead of int, won't it?
We will have to change the definition to use integer, right?
Okay, let's take some time. All right.
There is actually a generalized length that returns.
There is a generalized length.
Like
Yes.
generic, right?
And sort of the clever thing with that is if you return naturals that are like piano literals, in other words, they're cons, they're saying I'm adding one to 0, you'd actually get a lazy length result. So
Let's see.
you lazily compare the length of two things and find out that the length of one is longer without actually.
So I don't know whether it will overflow the stack.
Doing a lot of
Running
pairs.
all the whole.
Okay, so what is important here? I'm gonna keep erasing stuff, unfortunately. The important thing is this map. Okay, so let's keep it around. Let's keep map around. because, so did we get 45 minutes? Then maybe we should make a